Hello and welcome back for some more reinforced concrete design. Now that we know exactly how to look at bending, shear and deflection in reinforced concrete according to the Eurocodes, we'll summarise the design procedure in beams. The ultimate limit state design of reinforced concrete beams consists of producing member details which adequately resist the ultimate bending moments, shear forces and torsional moments. The serviceability limit state design of reinforced concrete beams consists of ensuring serviceability and adequate appearance under working loads. The main design steps consist of the preliminary analysis and member sizing, detailed analysis, and the design of reinforcement and serviceability calculations. The calculations of beam deformations at the serviceability limit state are based on the effective span. Eurocode 2 defines the effective span of the beam, LF, as the sum of the clear distance between the faces of supports, Ln, and the parameters A1 and A2, describing the effective support width on either side of the span. The effective support width is calculated as the lesser of half the width of the support and half the overall depth of the beam at support. The parameters A1 and A2 are defined for different support conditions in figure 5.4 of Eurocode 2, as shown on this slide. The layout and size of beam cross-sections are controlled by architectural details and clearances for machinery and equipment. The required beam dimensions consist of the section breadth, overall and effective depths, and nominal cover to reinforcement. Usually, the beam breadth is between a third and half of the beam overall height. When the beam breadth is smaller than 200 millimeters, it is difficult to provide adequate side cover and space for reinforcing bars. Member sizing is an iterative process, and it represents an integral part of member design. The member sizing procedure consists of the following steps. The initial effective depth of the section is selected approximately using a basic span-to-depth ratio suitable for the structural member considered. The section breadth is approximately selected to be between a third and half of the effective depth. The class of concrete is selected. The loads applied are calculated. The static analysis of the member is carried out and the moments and shear forces are calculated. The need for compression reinforcement is checked through calculating the parameter K and comparing it to the limit value. And then the required amounts of longitudinal reinforcement are calculated. The shear resistance of the section is then checked. The required shear reinforcement is calculated. The span-to-depth ratio is checked to assure that the deflection requirements are satisfied. And the overall depth of the beam is calculated as the sum of the effective depth, the cover to reinforcement, and the estimated distance from the outside of the links to the centre of the tension bars. Concrete is, by its nature, ideal for continuous structures. Continuity can reduce design moments and construction costs. Compared with simply supported beams, the span moments in continuous beams are greatly reduced, while the support moments are quite large. T-beams are ideal to deal with span moments, but they're not so good at supports when only the rib is in compression. Therefore, redistribution can be used to reduce the support moments. The corresponding increase of in-span moments is usually not a problem for T-beams. Elastic design with redistribution of moments can be considered as a halfway to the plastic design. In plastic design, collapse will occur in a continuous beam when a sufficient number of plastic hinges form. As load increases, the beam will yield where the moment exceeds the plastic capacity of the section. In the beam considered on this slide, plastic hinge forms at the middle support, transforming the continuous beam into two simply supported beams. The load can be increased further until the other hinges form a mechanism. In the beam considered on this slide, additional hinges form in the spans, and the beam collapses. Benefits of redistributing moments in continuous reinforced concrete beams include the reduction of moments at supports where the bending capacity is lower. Consequently, concrete sections and reinforcement requirements at supports are also reduced. The redistribution of support moments results in the increase of span moments. However, continuous T-beams generally have plenty of flexural capacity to deal with increased sagging moments. Let's consider a few additional design factors. At an exterior column, the beam reinforcing bar's resisting design moment must have anchorage bond length within the column. This means that the longitudinal bars should not stop at the column face. They should be bent and made to continue into the column, as can be seen in this picture. In monolithic construction, where simple support has been assumed in structural analysis, partial fixity of at least 25% of the span moment should be allowed for in the design. Reinforcement in the top of the slab must pass over the beam steel and still have necessary cover. Column and beam reinforcement must be carefully detailed so that the bars can pass through the junctions without interference. An example of a well-designed reinforcement at a beam-column connection can be seen in this picture. At a simply supported end, more than 50% of the span reinforcement should be anchored in the support. The necessary anchorage length is calculated using the equation given on this slide. As you can see, the anchorage length depends on bar diameter and the condition and strength of the bond between the steel bar and the concrete. Bending moments vary along the beam. This means that less reinforcement is required away from critical sections. Curtailment of longitudinal bars in beams is a way of reducing the area of tensile reinforcement at sections where bending moment is minimum or zero for the purpose of achieving an economic design. Here you can see the curtailment requirements adopted in the UK for longitudinal reinforcement in simply supported and continuous beams. In simply supported beams, 50% of the bottom reinforcement required in the span should extend to supports. This amount is reduced to 30% in continuous beams. Away from the support, the top reinforcement in continuous beams can be reduced to 60% and then to 20% of the required amount above the support. Further discussion on the curtailment requirements can be found in Topic 6, Part 1. Thank you for joining me in this session looking at reinforced concrete beams according to the Eurocode. Join me next time where we discuss the same, but for reinforced concrete slabs.